Okay, here we are, and we're going to begin talking about thermodynamics. And really, we're starting at the very, very base of kind of thermodynamics. And we're going to talk about heat and what heat is and what thermal energy is. And we're going to build to a point where eventually you might learn something about thermodynamics, maybe in AP physics or maybe in university, first year university. But for here we are in grade 11, we're going to study just the very basic stuff about, what is heat and what's temperature and what are all these things, so that we can begin to understand that instead of just saying, oh, in the conservation of energy, we'd lose some energy to heat. Well, we'd like to know kind of what that looks like. And so that's what we're going to do in this mini unit, which is really about 3 lessons long. So historically then, basically the development of thermodynamics kind of ran alongside and parallel to the development of the atomic theory of matter. So Robert Brown and Albert Einstein were two scientists that were studying different things, but they kind of, they're in reading each other's research, they kind of said, oh, what you're talking about over here is kind of similar to what I'm talking about over here, and perhaps these two things are related. And in fact, that's often how findings happen, is that two different people in two different parts of the world are studying similar things, and they use each other's discoveries to bounce ideas. So here's two crucial discoveries. First of all, concerning heat. And one of these things that we can quantify heat as is heat is basically the energy of motion. So it's the kinetic energy of matter at an atomic level, right? So when we get way down and we look at these molecules and particles that are kind of zipping around, their kinetic energy is what we call heat. Okay, so something has more heat if the atoms and molecules are moving faster and have more kinetic energy. Something has less heat if those atoms and molecules are moving less slowly, so have less kinetic energy. Also, the kinetic molecular theory, okay, had three postulates. Number one is that all matter is made up of small, constantly moving particles of atoms. Groups of atoms are called molecules. Yes, you've seen in grade 9 science, possibly even before. Number two, atoms and molecules exert forces on one another, and so that keeps them a certain distance apart. And that the distance between these molecules that we're talking about in postulate 2 and the strength of the forces are what creates our three states of matter. Okay, so these two things were crucial discoveries and led us to be able to talk about the states of matter and to talk about heat and temperature and so on and so forth. So, in your textbook, you have a description of the solid, liquid, and gas phases of matter. And I'm going to leave that for you to discover on your own. I would certainly recommend highlighting some of the key features of solids, liquids, and gases. Many of them you probably already know, but crack open your textbook and take a look at these three things, okay? Because this is required information, but we're not going to take time in the lesson to do it. If the molecules are moving around and have kinetic energy, we know that kinetic energy has to come from somewhere, right? Because we've talked about the conservation of energy. So these molecules are sitting here, they're moving around, zipping around, they get kinetic energy. Where's that kinetic energy come from? Like where do those molecules get their kinetic energy? And it turns out that potential energy, but in the form of electrostatic potential energy, so protons and electrons, kind of give them their kinetic energy. So thermal energy really has to take this into account as well. Thermal energy has to look at electrostatic potential energy, it's got to look at kinetic energy. So all of these things, in kind of like this grand way, are taken into account when we talk about thermal energy. Okay, so temperature, though, let's talk about temperature. Right, we know that when we're talking about a sample, some jar of liquid, and all the particles in that sample are in constant motion, right? But the number of molecules in that sample are huge, absolutely huge. How are we going to find the total kinetic energy of all those particles when, literally there's billions upon trillions of molecules in a sample? We can't find the kinetic energy of every single one of them. But what we could do is measure the average kinetic energy of all those particles, and that's what we call temperature. So temperature is a measure of the average kinetic energy of all the particles in a sample. And when a substance is heated, its volume increases, and this is kind of known as thermal expansion. Okay, and this is how a thermometer works, is that when a substance is heated, the kinetic energy of its particles gets larger, and the sample or the substance expands. Okay, thermal energy increases the kinetic energy in a sample, and this causes an increase in the average distance between those atoms and molecules. And this is basically how a thermometer works, right? And of course, the thermometer is a device for measuring temperature. So really what a thermometer does is it measures the average kinetic energy of the particles in a sample. Okay, so let's talk about how we measure temperature to begin with, because we're going to be talking about temperature a lot in this unit. There's 3 main temperature scales, 2 of which we'll use frequently, 1 not so much. The one that we're not going to use so much is Fahrenheit. Of course, this is the temperature scale that they use south of the border in the United States of America. It's named for Daniel Fahrenheit. He was German, and he's credited with this work around 1736. So, quite a few centuries ago. Of course, here water freezes at 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. Just to give you an appreciation for kind of what these numbers look like. And of course, this was calibrated using brine. So seawater was how Daniel Fahrenheit kind of calibrated his temperature scale. The Celsius scale is named for Anders Celsius. He was a Swedish scientist. And you'll notice not too much later, right? He's credited with kind of the Celsius scale in about 1744. And of course, you'll note this is not too much after. Of course, we know water freezes at 0 degrees Celsius, water boils at 100 degrees Celsius, and Anders actually created his using distilled water. So instead of brine, he didn't calibrate it to brine, he calibrated it to distilled water. And I should mention that even though I did say that they use Fahrenheit in the United States, most scientists in the United States wouldn't use Fahrenheit. They'd probably use Celsius. In fact, most of the scientific world either uses Celsius or they use this temperature scale called the Kelvin temperature scale. And William Thomson, who was given the title Lord Kelvin, okay, was British, and this is 1904. So quite a number of years later, in 1904. He kind of created or coined this Kelvin temperature scale, and he hypothesized that there was this absolute zero. And this was done in and around kind of the creation of some of the laws of thermodynamics, the first, second, third, 0th law of thermodynamics. And basically there's this hypothesis that there's an absolute low temperature. It's called absolute zero. And that's where all the motion of molecules stops. So the kinetic energy of these molecules is 0, and then of course that would be the lowest temperature you could get, and we call that 0 Kelvin. It turns out that 1 Kelvin is actually 1 degree Celsius, so they have the same size, and we can actually flip very easily back and forth. Now, before we kind of continue here, you'll notice this over here is a really nice little chart where you can see, this is basically the calibration or the conversion factors between temperature in Celsius and temperature in Fahrenheit and temperature in Kelvin and temperature in Celsius. So you can see that these little formulas, these are good to put on a formula sheet, or these are good to kind of commit to memory. Very oftentimes calculators will have built-in conversions, and so you'd be more than welcome to use those. So let's take a look at how we're going to use these in a problem. On a day when the temperature is 50 Fahrenheit, what's the temperature in Celsius and what's the temperature in Kelvins? All right. So here we have 50 degrees Fahrenheit. And of course, we know, if you've ever watched an American weather broadcast, you'll know that 50 degrees Fahrenheit is not particularly a nice day, but it's also not that cold of a day. 5/9 times the temperature in Fahrenheit minus 32. You also have to do bed mass here because this is inside of a bracket. 10 degrees Celsius is the temperature in Celsius when we've got 50 degrees Fahrenheit. All right, now what is this in Kelvin? Well, of course, Kelvin is equal to the temperature in Celsius plus 273.15. And we make this addition, and we've got 283.15 Kelvin. You'll notice we use degrees Celsius and degrees Fahrenheit, but when we come to Kelvin, we do not use a little degree symbol. Okay, that's a distinction between the three. Kelvin is simply a unit, and we just place the capital K there. Okay, so moving on. Let's talk about the transfer of thermal energy, because we know that thermal energy or heat can be transferred from place to place to place. Okay, so kinetic energy, heat is simply the kinetic energy of matter at an atomic level. So we're going to turn our attention to how heat or thermal energy is transferred from one object to another. So here we go. Place your hand. This is a little experiment that you can do right now. Place your hand on the surface of your desk or on the surface of the table where you're watching this video. Place your hand there. Now find something, basically the other hand or this hand or whatever, on the surface or the leg of a chair, something metal that's in the same room. Place one hand on the surface of the desk, one hand on something that's metal, if it's convenient. Which of those two objects is warmer? And of course, you would probably agree with me that, the table feels warmer than the metal object. And of course, what we'd have to say is that, yes, the surface of the desk feels much warmer. The surface of the table feels much warmer. But really, when you think about these two things, these two objects, they've been in the same room for the exact same amount of time, which is a long time. And so really, they're at the same temperature. So the desk and the chair, or whatever you have chosen to test here, have been in the same room for hours. So they basically have to be at the same temperature. So then the question becomes, why does the chair, or why does the metal object feel colder, and why does the surface of the table or the desk feel warmer? And the question can be answered by knowing something about the human body. And it basically is that our bodies actually don't measure temperature. Our bodies measure the flow of heat. Right? So metal will take heat away from us much faster than wood or the surface of whatever your table's made of. And so because of that, our body notices that heat is leaving our hand at a much quicker rate when it's touching metal. And so it feels colder, right? And this is kind of one of those interesting things about the human body, is that we really do perceive the flow of heat, and our bodies are made so that we can perceive the flow of heat. We've learned about the conservation of energy, right? That energy is not created, it's not destroyed, but it's transferred from one form until another. But we've always ignored heat. We've always ignored heat. Well, now we don't have to. Because in the mid-1800s, James Joule, who we introduced in the last kind of part of this unit, performed an experiment. And he kind of had a little system like this, right? He had this little system that showed that, okay, when I have these masses here, and I string them to this pulley system, and it goes up and down a certain distance h, basically I'm taking gravitational potential energy and I'm shifting it here and here and here. And what that's doing is that these are controlled, these are attached to this little spinner. And this spinner is attached to these little fins or paddles in the water. And so it spins the water around, it stirs the water. And what he noticed when he used a very sensitive thermometer was that, hey, when this mass drops and this mass goes up, and these things spin around, the temperature of the water goes up. Because what I'm actually doing is I'm increasing the molecular motion of the water, which is making the temperature rise. And this was one of the very first times when we were able to show that mechanical energy, which we've just studied, can be turned into thermal energy. And really, it's the same thing. Okay, so let's talk about just briefly how we transfer heat energy. Okay, and there's three ways. And probably one of the best ways to think about these three things is to think about your kitchen. Now, again, I'm gonna make mention of the fact that this is a reading assignment. This lesson is not done until after the video is done. You crack open your textbook and summarize conduction, convection, and radiation. Now, again, this is another topic where you probably have a pretty good idea about what conduction is. So when you think about the kitchen, where do you see conduction? And of course, you should be saying the stove top. We've got a piece of metal, and that piece of metal gets really hot, and then heat is transferred from that piece of metal into the piece of metal that creates your pot, and then that piece of metal heats the water that's in your pot. Okay, and that's where you see conduction. Convection is a little bit different. Where in the kitchen might you see convection? And of course, if you said the oven, you would be correct. Convection is basically where we use air currents to heat, right? So in the oven, a little element heats the air inside of the oven. And of course, then that air gets super, super hot and it heats whatever you've placed inside. And last but not least, radiation. And of course, a good example of where we use radiation to heat is the microwave. So each of these three are outlined in detail in your textbook. I leave it to you to read those things. And we're going to turn our attention now to quantifying heat transfer. So we'd like to take all of these concepts, the transfer of heat, and all of the things that we know, and we'd like to basically turn it into an equation, into a quantity that we can determine. So the amount of heat that can be transferred depends on three things. So let's think about the temperature difference. Okay, that's the first thing. If the temperature between a hot and a cold substance is increased, then more heat will flow. Right? Because we always try, heat always is trying to balance out two things. Okay, so if the temperature difference between a hot and a cold substance is increased, more heat will flow. Let's think about the mass of the substance. If a substance has more mass, it has more molecules to transfer thermal energy. So if we have a really, really big object that's really, really massive and it's at a certain temperature, lots and lots of molecules to transfer thermal energy. Okay? We also know, as we just experienced, that the type of substance plays a pretty big role in heat transfer. So just like the surface of your desk and perhaps the metal leg of your chair, different substances accept heat transfer to varying degrees. In general, metals will accept heat readily, and insulators will accept heat less readily. So the specific heat capacity, okay, is the amount of energy that's required to increase the temperature of 1 kilogram of a particular substance by 1 degree Celsius. And it has everything to do with this type of substance. Different substances have different specific heat capacities. And it's one of the fundamental ways where we can tell the difference between two substances. It's kind of like density, right? It's a quantity that's going to tell us about a substance, okay? This is the actual definition. It's the amount of heat that's required to increase the temperature of 1 kilogram of some substance by 1 degree Celsius. So each of these quantities determines the amount of heat that will flow into or out of a substance. And so here it is. The amount of heat that flows is equal to the mass of the substance M, measured in kilograms, mass of the substance, times the specific heat capacity, which is basically the type of substance, times delta T, which is the temperature difference between where it starts and where it ends. Okay? And so these are all the things. And of course, if you use Celsius, if you use kilograms, and if you use specific heat capacity measured in joules per kilogram Celsius, you get joules. as your heat energy. So let's do a couple examples, and then we'll call it quits. How much heat energy is required to raise the temperature of 1 kilogram piece of copper pipe from 25 degrees Celsius to 66 degrees Celsius? The specific heat capacity of copper is 3.9 times 10 to the 2 joules per kilogram degree Celsius. All right, so here's what we know. We know the mass, we know T1, we know T2, and we know the specific heat capacity. We can figure out how much heat energy is going to take. Okay, so using T1 and T2, we can work out the temperature difference, which is T2 minus T1. And this happens to be 66 minus 25, 41 degrees Celsius. Okay, so let's put all this together. Delta EH, so the heat energy, is equal to MC delta T, which is 1 kilogram times 3.9 times 10 to the 2 times 41. And when I multiply these things out together, I get 1.6 times 10 to the 4 joules. This is 16,000 joules, okay? Or controlling for significant figures, 20,000 joules. This is a lot of energy to heat this piece of copper and to increase its temperature by 41 degrees. That's a lot of energy, 20,000 joules, respectively, thinking about that. So let's take a look at another example. It's our final example for this lesson. A 0.5 kilogram block of iron at 80 degrees Celsius is cooled down. And we're going to remove 2.28 times 10 to the 4 joules of heat energy. So what's going to be the final temperature of that metal? If I remove this much heat, right? I started at 80 degrees Celsius. I'm removing this much heat. What's going to be the final temperature? Here's the specific heat capacity of iron. And so we can kind of take this in the same way as we did before. Here's M, here's C. And delta T, we don't know what T2 is. We do know what EH is, and this is important that we specify this. We've got to put a negative sign here because we're removing heat energy. We're taking energy away from the system. So this is negative energy, and so we need to put this little negative sign here. So that's one of those things. This is a key word, cooled. When something's being cooled down or we're removing heat, we need to throw a negative sign here. And so here's our formula, and we pop everything into place. Now you could just take this as T2 and delta T, and solve for delta T first, and then figure out what T2 is in the end. I'm going to do it all in one step. So instead of writing delta T and solving for that, I'm actually just going to put in brackets T2 minus 80. I'm going to collect like terms, and I'm going to move everything over to the other side, just like I've done here. And when I solve this, this becomes one number, and I add 80 to it, I get minus 19.1 degrees Celsius. So that means that if I remove this much heat energy from this block of iron at 80 degrees Celsius, I'm going to get it down to minus 19.1 degrees Celsius. And that's the beginning of heat. We'll see you next lesson.